You know, naming chemical compounds can sometimes feel like you're trying to memorize an entire dictionary. But what if I told you it's not about memorization at all? It's really about cracking a code. Today, we are going to decode the system for naming substituted benzene. And trust me, by the end of this, you'll see it's just a logical puzzle that anyone can solve. Let's get right into it. So here's our game plan. We're going to start with the absolute basics, the base name. Then we'll cover some really important exceptions and the rules for numbering. After that, we'll learn a common shorthand. And then we put it all together to name some seriously complex molecules. And you'll definitely want to stick around for the end, because we're going to build the ultimate cheat sheet. All right, let's start at the very beginning, with the foundation. What do we do when we have just one group attached to our benzene ring? Well, the first rule is actually beautifully simple. You just take the name of whatever group is attached, chemists call it a substituent, and you pop it right in front of the word benzene. So a nitro group gets you nitrobenzene, a bromine atom, bromobenzene. It is that direct. And since there's only one group, its position is obvious, right? So no numbers needed. Not yet, anyway. Okay, so just when we get comfy with a nice, simple rule, chemistry loves to throw us a curveball. See, in the world of naming things, sometimes tradition just flat out beats the system. Let's look at the big exceptions you just have to know. And this is a really crucial point. Certain groups completely change the base name of the molecule. A methyl group doesn't make methylbenzene. Nope, we call it toluene. An NH2 group gives us aniline. These common names are so widespread, so universal, that they actually overrule the systematic ones. The best way to think about them is as new parent names, new building blocks we're going to use from here on out. Okay, so this is where it starts to get more interesting. When we add more than one group to the ring, we suddenly need a system to say exactly where everything is. And that, my friends, is where numbering comes in. Now this slide shows the single most important rule of them all, the lowest locant rule. The whole goal is to number the carbons on the ring so that the groups get the lowest possible set of numbers. We call those numbers locants. So take a look. Should we call it 1, 3, or 1, 5? Well, the set 1, 3 is just lower. That makes 1,3-dibromobenzene the one and only correct name. You are always looking for the shortest path between the groups.
But what happens if you get a tie? What if numbering clockwise and counterclockwise gives you the exact same set of numbers? Well, that's when the alphabet steps in to be the tiebreaker. The group that comes first alphabetically gets carbon number 1. It's that simple. So here we have chloro and nitro. C comes before N, so the chlorine's carbon gets the number 1 spot. From there, we number towards the next closest group to keep all the numbers low. Then, for the grand finale, when we actually write out the name, we list the groups alphabetically.
Now, besides using numbers, chemists have a sort of nickname system. It's a common shorthand to describe how two groups are related to each other on a ring. Let's take a look at this so-called trivial system. This system is all about their position relative to each other. So compared to some main group X, the positions right next door are called ortho. One carbon away is meta. And if it's directly across the ring, that's para. But here is the critical, non-negotiable rule. This system only works for rings with exactly 2 groups. The moment you have 3 or more, you've got to go back to using numbers. And this table here just makes that connection crystal clear. 1,2-dibromobenzene is the exact same thing as ortho-dibromobenzene, or you'll often see it written as O-dibromobenzene. 1,3 is meta and 1,4 is para. They are literally just 2 different languages describing the exact same molecule. One is numerical, the other is more spatial. All right, we've gathered all the individual rules. We've got all the pieces of our puzzle. Now it's time to put them all together and see how we can systematically name even the most complicated-looking molecules. Okay, remember those exceptions we had to learn? This is where they become incredibly powerful. If your molecule has a group that gives it a special common name, like anisole here, that group's carbon is automatically and permanently locked in as position number 1. No questions asked. From that fixed starting point, you then just number the rest of the ring to give the other groups the lowest numbers possible. So for this one, we start at the anisole group, number towards the closest chlorine, and we get the number set 1, 2, and 4. This example right here brings it all together. First, we have to apply that lowest locant rule. We could try starting at any of the groups, but if you work it out, only starting at the methyl group gives us the lowest possible set of numbers, 1, 2, 4. Any other starting point would give us a higher set. So we've got our numbers.
Then, to write the final name, we ignore the numbers for a second and we just assemble the name alphabetically. Chloro comes before methyl, and methyl comes before nitro. Put it all together and you get 2-chloro-1-methyl-4-nitrobenzene.
Now for a quick perspective shift. What happens when the benzene ring isn't the main character of the molecule? Well, if the ring is attached to a longer carbon chain, the roles are completely reversed. The long chain becomes the parent name, and the benzene ring is now just treated like any other attachment, and when that happens, it gets a new name, phenol. We can also work backwards, which is pretty cool. A name is really just a set of instructions. For 4-ethyl, 1-fluoro, 2-nitrobenzene, we start with the root, benzene. The name tells us to put a fluoral group at position 1, then a nitro group at position 2, and finally an ethyl group at position 4. It's like a precise blueprint for drawing the molecule. And notice again how the name itself is written alphabetically, ethyl, fluoro, nitro, even though the numbering followed that lowest locant path.
Whew, we have covered a lot of ground. So let's do ourselves a favor and consolidate everything we've learned into one final practical blueprint that you can use anytime you need it.
And here is the master framework. The best way to think of this is as your decision-making algorithm. For any molecule, you start at the top. First question, does it have a common base group? If the answer is yes, you follow the path on the left. That group gets number 1. If the answer is no, you go to the right, and you just number for the lowest locants. The next step checks for any ties, and if there is one, you just let the alphabet decide. This flowchart is your guide to getting the correct name every single time.
And this is the ultimate takeaway, your final cheat sheet. You've got the essential base compounds to remember, a refresher on the ortho-meta-pair system, and the 3 golden rules. 1, always prioritize the lowest numbers. 2, give those special base compounds priority. And 3, use the alphabet to break any ties. I would seriously recommend taking a screenshot of this. With this blueprint, you now have the tools to decode any substituted benzene you come across. The only question left is, which one are you going to name first?